Okay, good morning, everyone. Welcome to EX 151 251A, Introduction to Digital Design and Integrated Circuit. So for the last, I guess, few lectures, we did a review of the RISC-V ISO and data path element and pipelining. Hopefully that has been useful for you folks to, I guess, remind what you folks have learned in 61C and also get ready for the project. We'll talk a little bit more about the course logistic as we are going to start the project phase very soon. So since we wrap up the RISC-V, we're going to start a new module of the 151 course content. We're going to start, I guess, going down. We'll talk about the stack later, going down the stack and to talk about how we build transistors, how it actually works, right? How those like low-level elements and how they are actually eventually reflected in our digital abstraction, right? So this is, I guess, typically where topics gets a little bit unfamiliar with for students, but we have like taught these courses through generations, and we have really think about how to actually make the concept a lot more approachable to students, especially with a more programming like CSE background. So let's just go with it and see and learn together, and feel free to ask questions. And this is always a time that everyone learn together to really explore the different ways of thinking about transistor and the semiconductor industry. So before we get course content, I was thinking about this slide. This is actually the exact slide I used in fall 2021, also in 151. And this is actually when Intel first, I guess, announced their roadmap to more advanced manufacturing. And back then, they were actually targeting 2025. So, right, so this is exactly 4 years later, right? So it'll be interesting to review, I guess, what they have projected and where things are, right? So for folks who remember around 2020, 2021, that's around the time when Intel started really thinking about advanced manufacturing, especially domestic advanced manufacturing, and have like more concrete roadmap in terms of how they actually want to support different semiconductor needs in the US, and also how they advance to more advanced nodes. For a lot of the folks who are actually more familiar with some of the courses we taught here at Berkeley, this node is probably very familiar with. This is called Intel 22, but it's the same as Intel 16. So this has been the FinFET technology generation we have been using for our tape-out class. And it has been, I guess we're very grateful for the donation from Intel, but it's also one of the leading edge FinFET technology back then. And it has been really fun to explore a lot of the different components and the characteristics from the more advanced technology. So back then, Intel had this projection, and one of the biggest components they introduced is this kind of angstrom era, and they actually changed all the new unit from nanometer to actually the A. So angstrom is basically 10 nanometer, right? So far we have been going down like 16, 10, 7, 5, 2, right? But we'll get 2. There are just not many numbers you can play with. It's a little bit awkward to say it's like N1.8, right? It's just a mouthful. So they switch the unit instead of 1.8, it's like 18A. Instead of 1.4, it's like 14A. So that's like the new node name to actually more advanced node. Back then, Intel actually introduced two very significant changes. We'll talk a little bit more when we actually get to the lecture. One is actually migrating from FinFET to what do they call like ribbon band, or we'll talk about some other people also call gate all around. So it's actually having like all the like different, instead of just things, you can actually create almost like circles that wrapping around the gate to have actually better control over the channel. So that's like one of the very significant changes since the FinFET generation. Another very significant change, it'll be hard to tell here, is like the metal stack over there. So what they introduced is, actually anyone know what they introduced? Intel introduced? For people who are playing with 18A? Adam?
Backside power delivery.
Yes, backside power delivery. What's that?
Oh man, I don't totally understand it, but like, so like there's the layer that has like the transistors, and there's metal and metal and metal, and like inevitably the metal all gets congested. And so if you can put more metal on the other side, you can move power to stuff without taking up valuable routing
Exactly. So when we think about a wafer, when we do actually transistor manufacturing, right? It's always okay, we start from transistors and all the metal layers, right? But it's always like a mix of like power delivery metals and all the signal metals. So what Intel actually did first is actually move some of the power delivery metal layers instead on the top of the wafer, actually to the backside of the wafer. So it's like better separation, and you have actually the dedicated power metal delivery network and also the signal routing network, so less congested. But definitely you actually need to actually apply or print your circuit on both sides of the wafer, right? So that's the backside power delivery, and that's also being introduced in the Anstorm era. And this is also becomes the norm when actually like the TSMC is doing the same thing, trying to do the same thing, and Intel is also doing the same thing for the more advanced technology. So a lot of like, I guess, attentions on basically 18A. We talk about some earlier news on 18A, and also more recently, Intel's next node is actually 14A, right? So this is actually get to a lot more advanced technology node. There were a lot of, I guess, rumors on the yield of the new technology generation. I guess I was just checking last night. It seemed like 18A may actually get to mass production later this year. There might be actually product released in 18A. Well, fingers crossed. We'll see where things are. But 18A is basically the current generation. There's also a lot of, I guess, attentions on 14A, which is the next generation, and how that can be used for wider customers there. And we also heard, I guess, the past few weeks, as there have been a lot of news around Intel, right? Signing new agreement, collaboration with Intel, NVIDIA, and even potential collaboration with AMD, right? So all of those could potentially be Intel fabs customers. And it's going to be interesting to see, instead of monopoly in the fabrication industry, there are like more, hopefully healthy competitions between Intel and TSMC and also Samsung in this kind of more advanced technology node, right? So now looking back, it's actually pretty impressive that they actually follow the projection. They are trying their best to deliver like the more advanced technology node, but this is also a very expensive and very competitive market, right? Everyone is eyeing towards a more advanced node, and all the customers also want to get access to actually more advanced node. So there's a lot of demand. The question is that whether the fabs, in particular, I guess the leading fab these days, Intel, TSMC, and Samsung, can actually deliver the more advanced technology. So things are actually predict pretty well. I guess this is more than technology side. There's like yield side, there's marketing side, but this has been the roadmap for the past 4 or 5 years for more advanced manufacturing. So with that in mind, I really like the abstraction layers Ben put together, right? So one thing you notice in this class, we're jumping up and down across the abstraction layers to understand the complexities of the semiconductor industry, and also especially the digital circuit design. For the past couple of weeks, we have been mostly a little bit on the architecture on the RISC-V ISO side, but mostly on the microarchitecture side, right? How we think about data paths, especially how we think about pipelining, what are the different hazards exist in the data path. Moving forward for the next 2 to 3 weeks, we'll be actually going down the stack and really thinking about transistors, all the different building blocks, right? What are they? How they are being abstracted in the digital abstraction layers, but what kind of behavior that we still care? How do we reason about timing? How do we reason about latency? How do we reason about power, right? Especially for folks in the ASIC lab, you have been actually playing with different power, like timing report, right? What does it mean, right? What are the differences across different generation of technologies and how they are actually really being reflected in today's digital stack? So we're going down the stack and really thinking about how transistors and how the different components are being designed and connected together. So in particular, think about things we like to cover. We'll start from transistor. We'll talk about the switch model when we think about MOS transistors and what we mean by having both NMOS and PMOS and how they are related and are different from each other. And after that, we'll go to how we actually use different transistors to build gates. We have been playing with inverters. Inverter is always a good example to get things started with. And then how we actually think about more complex gates in thinking about both the PMOS side, the pull-up network, and also the pull-down network from the NMOS side. It's always pretty fascinating when we actually think about transistors, especially we talk a lot of this kind of fancy architecture, they are like very different designs. But if you think about the semiconductor industry, right? Things haven't like everything happened within the past century, right? So it's really when we think about the first transistor being designed from the Bell Lab and all we actually get to the integrated circuit and all to this kind of mass production of the entire semiconductor industry, right? Majority of things happen really in the past, I guess, 7 or 8 decades, but it's actually pretty impressive to see how things have advanced and what do we mean actually how we go from this kind of really, really low level individual transistors to all the way to this kind of complex system that we're designing that actually packed millions and even billions of transistors together to today's system. But things actually start from actually very important fundamentals. And whenever I tell this class, I think it's always useful to review the fundamentals. Most of the fundamental already covered in high school, right? This is really just like review things like the principles or the intuition that will be very, very important when you actually approach transistor level dynamics, right? A lot of those is really basic electrical behaviors, but then you will see actually the same being reflected when we talk about transistor behaviors, right? So most fundamental thing is really just Ohm's law, right? So how we actually think about voltage and current when they actually across resistors, right? If we think about resistors, right? So we have a resistor here. We have a resistor here. Let's see whether I can get mine. We have a resistor here, and we have like the voltage across the resistors, right? Once there a voltage applies, the current actually flow through the resistors. When we actually think of the behaviors, right? In particular, how much current actually flowing through the resistors, it's basically this IV characteristics, right? And when we apply different voltages, actually the current across the resistors actually increase, right? So it's basically the more voltage you apply, there's more current actually floating across the resistors. That's basically Ohm's law, right? When you have actually the variable resistors here, when you have variable resistor here, the resistance actually change based on the current, based on the voltage actually being applied here. Okay, I'll just leave that here. Based on the voltage that's actually being applied here, and that's basically variable resistors. But when we actually think about physical resistors, right, it's basically a type of material at a time a type of material that can be manufactured with different components that follow particular dimensions, right? If we think about the resistivity of different resistors, how do they actually connect it with each other, right? It's basically related to its intrinsic behavior, how like what's the resistive factor that it has, and also the dimensions, right? What are the different dimensions of the devices, and that also lead to different behaviors. So if we think about the resistors here, my Apple Pen is running out of battery here. But if we think about the resistance here, right, it's related to the resistivity, right? The material property of the particular devices that are actually being used to conduct a current, and also related to the length of the behavior of the component, right? The longer the component it typically has like more higher resistance because things need to travel much longer, right? There are a lot of things that could actually limit how fast the current is actually floating. So it's actually the longer the device is, it typically have higher resistance. It also related to the cross section of the device here, both the width of the device and also the depth of the device, right? You can think about the cross-section area, right? If you have actually a big channel, it's like very wide, it's actually easier for current to flow through, right? So you typically have lower resistance, but it's like very narrow, very dense, right? It's actually harder to flow through. It typically has higher resistance, right? So that's how we think about resistance of the particular device. It's related to the resistivity, like it's a material property of the device on its own, but also related to the physical dimensions, right? How long it is. If it's longer, typically higher resistance, and how big the cross section is for both the width and also the depth. In most of our discussion today, we'll mostly focus on the width. You can see like how you use width as a representation of the cross-section area, and the bigger the cross-section area, it's easier to flow current around, and we typically have smaller resistance. Make sense? Sounds very familiar with? Okay, so with that in mind, we talk about the single resistor behavior, but also when we actually pack multiple things together, right? How do they actually interact with each other? When we have actually two resistors, right? When we actually put them in serial, we have, it's basically make things longer, right? We have higher resistance when both actually combined. So it's basically doubling the resistance. But when we actually put things in parallel, so now there are like multiple paths things can go through. So the overall we have lower resistance, right? So I have more current that can go through. And that's basically related to like the dimension that we talk about is like doubling the width, right? So we back to the IV characteristics of the device that we have in mind, right? If this is like default behaviors, you will actually double. We have like putting two resistors in serial, it typically to higher resistance and for the same voltage, lower current, right? And when we actually put more in parallel, it means lower resistance. And for the same voltage, we have higher current, right? Makes sense? Matches the intuition overall? Okay, then we'll see how this actually being applied. We actually talk about transistor dynamics. So many of you should have seen transistor behaviors in 16B or 105 a little bit, right? So we talk about transistor as a switch model, right? We talk about the three terminals later, right? But when we actually apply voltage, when the voltage is like high enough, the switch is actually on and we can actually have current flow through that. But it will actually, when we don't have current applied to the channel, to the gate, the switch is off and there's no current flow that, right? We'll talk about a little bit later, but this particular dimension, the gate actually control the switch. And in particular, it's actually the voltage between gate and the source. The delta between those two terminals actually control whether the switch is on and off. So when it's on, it's just like a resistor. When it's off, nothing actually going through. So this is a very basic switch transistor as a switch model. In particular, I guess, voltage applied to the gate, in reality, what it really does is really charging and discharging the capacitors, and that's how we actually have a channel conducted between the other two terminals, between drain and the source, to actually make current flow through that. We'll talk a little bit more in details, but physically, it's really charging this channel capacitors, so that we can create a conducting channel so that current can actually float from the other two dimensions. So at a very high level, when we actually think about transistors, right, it's really just a switch. Again, when the gate voltage is actually small, the switch is off, so nothing actually goes through. When the gate voltage is high enough, actually the switch is on, we can have the current flow through. So this is like very high level MOS transistor as a switch model. But how does that really work, right? How does this kind of particular gate voltage actually control whether the channel exists, whether the channel is actually conducting so the current can flow through that? If we look inside, when we think about transistor, we always talk about CMOS, right? We talk about the C part later. When we talk about MOS, what does MOS mean? It basically mentions the different layers existed in our transistor fabrication process. And fundamentally, we have a mix of a metal and oxide and then semiconductor layer so that we can create a capacitors that can be charged and discharged to create a conducting channel between the other two dimensions. Right, when we talk about transistor, it's always three terminals. We'll talk about the three terminal later, but one terminal is a gate terminal, right? So gate terminal controlling whether we can create a channel between the other two terminals so that the other two terminals can be connected or disconnected, right? So that's a three terminal device. One terminal is controlling whether things are on and off. And then when it's on, we can form a conducting channel between the other two terminals to actually turn on or off. the transistor. So that's basically fundamentally what the transistor trying to do, right? So here we're showing, like we'll talk about why it is NMOS later, right? So, but this is basically NMOS transistor with metal oxide and the semiconductor layer. We talk about the three dimensions, three terminals, gate, and the drain and the source to create. Gate is a controlling terminal or on and off. Drain and the source, the other two is a conducting terminal. When things are on, we can create a channel to actually make current flow. And when we think about transistors, they have actually dimensions, right? The size of the transistor, how wide it is, how long it is, right? So if we actually look at like a cartoon of the transistor diagram, right? So this, I guess this is a cross section. This is a more top-down view, right? So you look at the top-down view. Oh, let's do the cross section first, right? We talk about gate, I guess metal outside. The metal layer is basically referring to the gate layer, right? We talk about gate is a controller, right? So gate is that controlling whether things are on and off, right? So gate is referring, the metal layer is referring to the gate, or sometimes you also hear people talking about polysilicon. Those are different ways you can construct the gate here, right? So gate is basically on top of that to control whether the other two terminals can be connected or not. The other two terminals are basically symmetric, typically viewed as one is the source, one is the drain, right? The source basically almost feel like a water faucet, like the gate is a faucet itself, whether it's like on and off. Whenever it's on, source is where water actually starts flowing to the drain. Drain is like draining the water, right? You have a source, you have pool of waters, and then you're trying to flow like electrons or hose, which is a water here, to actually float from source and the drain. Right? And fundamentally, what we are trying to do with transistors is basically by having this gate and then oxide here and the semiconductor layers, we can actually form a capacitors, right? By having a capacitor, we can actually create a conducting channel on the other side so that things can be on and off. We talk about dimensions, right? So when we actually think, we look at this, it's easier to look at this way. When we think about actually a transistor, there's also the dimensions of the conducting layers, right? So here we talk about length of the channel, right? So here is basically the width of the gate, right? How wide that gate is. For a while, when we actually talk about semiconductor technology node, it's actually referring to the length of the gate, right? How wide it is, right? It's getting smaller and smaller. So shrinking transistors, but it's very hard to shrink these days. But here is a gate dimension. And also the width dimension, right? How wide this channel is, right? We talk about the resistance of the channel, right? So it has the length of the channels, but also the width of the channels. This is at a very high level, like the three terminal devices and how it is actually mapped into a physical transistor behaviors. We'll talk about how we actually form those channels, but those are actually three terminals. Again, gate is actually the controlling part applied to the metal layer or the poly layer, and then the other two terminals are forming a channel between source and the drain. A little bit dry, but does it make sense at a very high level? We'll talk a little bit more how we zoom into like low level details later. Any questions, thoughts? So far, so good. Okay, so this is basically the N-type transistors. And I guess similarly, we also have the P-type transistors at a simple level instead of just applying gate here. We have a circle here, meaning it's actually negate from the NMOS. The devices are really symmetrical, but it's just whether it's actually for NMOS, electrons are floating from source and the drain. For PMOS, it's more like holes are actually floating from source and drain, just relatively different voltage potential between source and the drain, and that lead to different behavior. And specifically, like we mentioned, for NMOS, we have actually more electrons, so that's why we call it like N+. So there are like a lot more electrons in the source and the drain layer. We dope it with actually more electrons here, but for PMOS, it actually has more holes and more positive charge that actually carry the current. Makes sense at a very high level? Okay, great. So that's, I guess, a very high level, the different terminals and how they are conducting and disconducted. Let's take a deep look, deep dive into how things actually work, what really happened at the transistor physical layer when we apply different voltages to different terminals, right? So here, how NMOS transistor actually works, right? So we talk about the transistor terminals. We have 3 terminals. Here is our gate. We have source. For NMOS, it's actually N-type, like it has a lot more electrons here. It's like N-type doped. And for PMOS, it's the opposite of that. It actually have more holes or P-types there. We have 3 terminals. One is a gate terminal. We mentioned the gate is actually applied the metal or the poly layer here to form, we'll see later, to form actually capacitors in our transistors. And then we have the other 2 terminals, source and the drain, that actually form a current that's floating from in the transistor layer. So I mentioned earlier, right, when the gate voltage is low, right, the gate voltage in particular is actually less than the threshold voltage. We'll talk a little bit more what the threshold voltage is, but when the gate voltage is like low, let's say 0, nothing going on, right? It's a capacitor, things are not conducted, there's like no channels, no channel actually existed between the drain and the source, so there's no current actually floating through our transistors here. Let's see what happens when we actually apply voltage to the gate terminal. So when we actually apply voltage to the gate terminal here, so now our gate terminal actually have a high, has high voltage here. What it really does is that it actually has more charges being accumulated on the metal layer, right? We talk about it's basically like almost like capacitors. We have the metal layer, we have the oxide layer, we have the semiconductor layer, right? When a lot of charges actually accumulated on one side of the capacitor, what will happen on the other side of the capacitor? There are a lot of positive charges happen on one side of the capacitor. Will the charges actually flow through the capacitor? No, right? Capacitors things actually don't flow, right? It's accumulating charges. But once there are lots of positive charges on one side of the, I guess you can think about capacitor metals, what it does is actually attracts a lot of negative charges on the other side, right? The other side of the capacitor, the other side of the metal is actually attract a lot of negative charges there. To the extent that once it's high enough and wait a little bit, it has enough, in this case, electrons that they can actually form a channel between source and the drain so that things can actually float around. Mm-hmm.
But the negative charges from the flow or from the M plus drains?
The negative charge is actually from the body of the transistor, the basically the body. So here is the body, so the P negative part. So it actually attract enough electrons to form the channel, and once it connects the channels, then things can actually float in from between the source and the drain there. Something there. Because we have a positive voltage applied to the gate. The gate voltage here. It's just I'm applying positive gate voltage to the capacitor. I'm charging the capacitors here. You can almost there, like, let's say you have like basically VDD applied here. So now I have this is a capacitor. I'm charging my capacitors. I'm actually getting more like a positive charges on the top metal layer of my capacitors. Right? It's basic. You can just think about it's connected to VDD now for the gate. Right? That's how we actually get a lot more positive charges on the gate voltage. Make sense? Any other questions? Mm-hmm. Oh, we haven't got there yet. So far we're mostly talking about we're applying gate voltage there so that we can create a channel, things are conducting. But to actually have things actually floating between drain and the source, you need to have actually the potential difference, right? There need to be voltage difference there. So to have current flow, so here electrons are flowing from, again, negative charges are flowing from source to drain. So the current in the positive side is actually from drain to source. So when gate is conducting, when a positive charge is applied to the gate, to actually have current flow through, we also require the potential difference between drain and the source. That's where drain voltage comes in. So you also require the drain voltage to have a drain side has a higher voltage so that we can actually have current flowing from between drain and the source. So there are two voltages are actually applied here. We talk about the gate voltage to actually create the channel, and also the drain voltage to actually have things actually floating through the channel.
Sorry, the light green is just electric as well.
Oh, the light greens are actually doped here. So for N plus, you can think about it's like start with the base transistors, and we dope a lot of electrons, a lot more like electrons to the N to the. Oh, you mean this green?
Yeah.
Those are just electrons. Those are channels being formed there. Those are not doped. Those are actually like electrons attracted to the channel, to the top of the body. So the P well, so we go back here. So we talk about when we actually manufacture semiconductor, actually have talked about that when we actually manufacture semiconductor devices, right? So this is a body layer, typically neutral, or like we talk about a little bit P negative for NMOS or the other way around. This is a body layer for source and the drain. Actually, during the manufacturing process, we actually doped like either with like more electrons or like less electrons for PMOS, for NMOS and the PMOS. So those are actually particular doped to actually create those source and the drain regions.
Talk about current. Or electron flow.
Yeah, so that's a little bit. So for NMOS, I'm talking for directions. I'm talking electrons are moving. So when we talk for NMOS, when we talk about source, so conducting material always flow from source to drain. So that's why source is called source. For NMOS, electrons, the negative charges is a conducting material there. So electrons are floating from source to drain for NMOS. Negative charges floating from source to drain. But for current is always from positive to negative. So the current is floating. When we think about current, it's actually drain to source. It depends on the carrier of the components here.
So it's like the body is, do we consider it as like an insulator? I'm thinking like if VG was greater than 0 and there was no channel, because VG was 0. Why wouldn't
when VG is 0?
Yeah, VD was greater than VS.
So what if VG is 0, but VD is like greater than 0 here?
The current is low because the body like the channel doesn't exist. There's not enough carrier to have the channel conducting, right? So that's exactly why even you have I guess voltage difference between source and drain, you still need to have gate to apply there to actually formulate a channel. I guess this oxide layer is an insulator layer. So that part is an insulator, but here you can actually, I guess you can bias it and then you can extract the electrons there to form a channel.
So writing the whole like various does it like really change like the flow of that current?
You mean the width of the channel, whether this width?
How wide?
Right, let me just have a different color. So I mean the width of the gate here, whether it changes. Yeah, that's a good question, right? How does the gate length actually change the behavior here? We talk about resistor, so like, yeah, how does the gate length change maybe the resistance of the transistor?
it's going up, right? We talk about the resistivity. Once the channel is longer, resistors, you just like need to take longer to actually flow through, right? Like you need to make more effort to flow through. And I guess we talk about resistors. How about capacitance? How does the gate length impact the capacitance of the transistor? It's going up, right? You have like bigger area now, right? So you can actually attract more charges, right? So you can really think about this is really just like a capacitor here. And by applying, again, what we discussed, voltage here, we can form a channel, and then that becomes the resistor we talk about, right? And the L is gate length is basically the length of the resistor. Good discussion. So we talk about the three terminals. We mentioned actually when gate voltage is applied, we have the channels. That's the first condition. And then we also have a drain voltage greater than source voltage. So we can actually have current flow through between drain and the source. So let's say we keep growing, keep increasing the drain voltage, right? So here, gate voltage is always conducting, right? So gate voltage is conducting, we have a channels, and here is what we talk about the drain voltage, right? This is roughly basically when we think about the IV characteristics. We think about the voltage, again, between drain and the source, right? So like earlier we talked about the IV characteristics for a resistor, right? Think about the voltage between drain and the source, and the current actually flows through the resistor, right? So this basically like a resistor. When you have higher voltage, higher drain and the source voltage, you get higher current because this is a resistor. That's the transistor is behaving like a resistor here, right? What if, and let's say we have actually different, you will actually have, okay, the animation is, so you will actually have different gate voltage, right? Well, let me slow down a little bit. So let's say, what if we actually increase the gate voltage? So now this is a resistor. Now we are actually trying to increase the gate voltage. How does that change the current actually flowing through the transistor? So we already form a channel. Now one of the conductors are connected to the gate voltage, and I'm increasing the voltage I'm applying there. How does it change? It's going up because
the effective resistance of the channel is lower, because it's wider.
it's wider because yes, you can think about it's like you have more electrons. The channel is bigger now, right? So you attract, because you have higher voltage on one side of the capacitor, you actually attract more electrons on the other side of the capacitor. You have a more like wider conducting channels. So when you actually have apply higher gate voltage here, we see actually increasing current for the same drain and source. So we have three channels, right? So now I'm modulating the gate voltage. So when we actually increase the gate voltage, we're also seeing the higher current for the same drain voltage. And we keep increasing until the gate voltage reach VDD, the highest voltage of the circuit. So that's how it scales, voltage scales when we're actually modulating the gate voltage. Now let's get back to the drain voltage, right? We mentioned the drain voltage is to create drain and the source voltage difference is to actually create the current flowing through. So let's say we keep increasing the drain and the source voltage, and then it's basically act like transistors. What if we actually increase the gate voltage to the extent that actually get very close? So those two terminals actually get very close. The voltage difference between the drain terminal and gate terminal gets so close, even actually smaller than threshold voltage. Anyone have seen that before? What if the other two terminals have actually been so close? Have people heard like the pinch-off region for semiconductor? Ryan, what does that mean?
You get less current.
Right, so why it saturates at that point?
The channel width doesn't really grow anymore. So basically don't get any benefits for a black voltage.
Right, more like at a very high level, exactly as Ryan said, right? So when the voltage difference between those two terminals actually get close enough, you can almost think about near the gate and the drain part of the transistor. There's basically create like what people call pinch off region. It's like where things are sort of saturating. The channel doesn't get wider. It's like a fixed channel no matter how high of the voltage you're applying. That's always like the fixed channel that you need to go through. And when the behavior happens there, this basically get to a what people call saturation region. It's basically when the voltage difference between gate and the drain is so small, you are basically limited by the, I guess, a conducting area between drain and the gate to the extent that no matter how high of the current voltage you're applying, it's not changing the channel behavior. It's always a fixed saturation current that's actually floating through the channel there. Right, so that's basically as we talk about different phases of the behaviors. When gate voltage is 0, it's basically completely off. Right, when we apply gate voltage, we get to this linear region. It's basically behave like a transistor, like a resistor, but until the drain voltage gets so close to the gate voltage, that's actually when it's basically this conducting channel is not going to change no matter how high the drain voltage is going to apply. And this get to what we call a saturation region of the transistor behavior. Things make sense? Very high level, the behaviors, all the channels. And similarly, actually, when we actually apply to a different gate voltage, we also see different gate voltage have different, I guess, limiting factors in terms of how big the channel is. And that's basically almost behave like what we talked about earlier is here, right? Different gate voltage have different channel, can conduct the different channels. And then overall, once the drain voltage get high enough, it get to the saturation region. So just a quick recap, when you think about transistor behaviors, we start with is 3 terminal devices. We have gate, which is basically controlling whether transistor is on and off. And then when it's conducting, we can actually at a very high level as a switch, we can create a conducting channel between drain and the source. At a very high level, the first level abstraction that we really care about is basically almost act like a switch, right? The gate is controlling whether the switch is on and or off, and when it's conducting, it's basically current flowing from drain and the source, and this transistor will act as a resistor. We talk about the 3 different, I guess, behaviors when we think about transistors. First is when gate voltage is low, right? In particular, less than threshold voltage. When it's that low, no matter how high, what is the voltage difference between drain and the source we mentioned earlier, as long as the gate voltage is not applied, there's like no conducting channel existed between drain and the source. So the current is 0. Nothing is going on. Right? But when we actually have the gate voltage applied, and then the channel is conducted, and then this basically the linear region is basically act as a resistor until when the drain voltage get close enough to the gate voltage, and that get to the saturation region, right? So that's basically the 3 different behaviors when we think about transistor, right? At a very high level, it is a switch limited, controlled by the gate voltage. Even when we think about resistors between drain and the source voltage, there's always this kind of more linear region. It just acts as a resistors. And then there's a kind of more saturation region where things are actually saturated no matter how big of voltage we're applying here. So those are basically the 3, I guess, behaviors when we think about. So far the discussion has been NMOS transistors, and then when we actually, of course, we can also modulate the gate voltage. Different gate voltage would also lead to different channel behaviors, and that would also lead to act more like a variable resistors with different gate voltage applied. You have actually different resistance of the channel here. Things make sense at very high level, NMOS behaviors here. So if we look at now, I guess NMOS transistor, we talk about current and voltage characteristics, right? So again, the three regions we mentioned, once the gate is off, nothing actually flows through. And then there's like more linear region and then more saturation region, right? And the current flowing from drain and source is dependent on different, the drain and the source voltage. It also dependent on the gate voltage, right? Because gate is actually modulating how big the channel is, right? So it's dependent on both the drain and the source voltage and also the gate voltage. In particular for gate voltage, right? If you now look at the behavior, how the current is related to the gate voltage here, right? So we mentioned that before it's actually reached the threshold voltage between gate and the source, is nothing is going on, it's zero, is the same region as we discussed here. But once the gate voltage is high enough, then this is basically a behavior that we're observing on how big the current is actually flowing through that. And I think you will talk more about the different behaviors and how it actually scale with channel length, all the different factors, probably in 106 or even 130, you'll probably do a very deep dive into that. For a lot of abstraction, we're talking about maybe for older generation technology, this is like more quadratic. You can think about like current when you're actually charging and discharging capacitors, it's more like quadratic relationship. For more advanced technologies, there are a lot of non-ideal behaviors existed. You can almost think about getting more like a linear relationship. When we think about current, again, this is current with a drain node, and this is current associated, how it changes with a gate node. Mm-hmm.
So based on the curves, does that mean it doesn't matter what GPS is, it always takes a step out of time to charge?
Is that the case? So if we look at this, right? So first, the amount of time to charge is basically the current, right? Flowing from between drain and the source. And the current here, IDS here, it does change with the gate voltage here. Right? Different gate voltage, you will actually have different current here.
The time it takes is the
Oh, you mean how fast? How fast the circuit charge and discharge?
yeah.
Let's say you have fixed amount of electrons there, like stored in your capacitor, or charges stored in your capacitor.
Oh, okay.
If you have higher current, it's charge and discharge faster, right? Current, like electrons actually flow through your capacitors much faster when you have higher current. All the high school memories are back.
Yeah.
Charging, discharging capacitors. You have like charges stored in your capacitors, right? If you have higher current, you can throw away them really, really quickly. But if you have smaller current, it takes a while to actually accumulate those charges, right? Right, that's what we mean here. And so the current here, we'll talk about the speed implications there, but it related with both the gate voltage and also the drain voltage. So that's 3 terminal devices related with both terminals there. We're talking about more like in this kind of more ideal behaviors, but when you actually get more realistic behaviors, nothing is like as flat or as we discussed, there's always this kind of things are still like kind of increase a little bit, especially when you actually get like the channel length actually like less modulated. So there's like still non-ideal behaviors that lead to still a little bit increase with when you get to like shorter channels and also less resistance. So things can still increase a little bit, but those are still like general like trend when we think about transistor behaviors. Yeah.
Sorry. 7 just means like the channel length away.
Yeah, so we're talking about, so I don't think you folks are using 7 nanometer now. You're folks using a more 130 Skywater 130 now. So for older, we have been using the ACEP7, which is I guess the open source advanced technology node. It's actually a fake technology as it's useful for education, but it's not actually something you can fabricate. So here, 7 nanometer, you can almost think about, it's hard to pinpoint exactly where 7 nanometer is, but you can think about it basically very short channels. Like the length of the channel we discussed earlier, we get to actually more advanced technology node. You can think about it's like very short channels. You get actually very short channels. There's still like different non-ideal effects that exist. They're like all the non-ideal behaviors when you think about channel length. A lot of like very low level behaviors here. Okay, well, so far we have been mostly talking about NMOS, right? How about PMOS, right? We talk about NMOS, we have the gate, we apply positive charges here, and then we have current actually flowing from drain to source, but in reality, I guess it's more like electrons actually flow from source to drain, right? So when we actually get to PMOS, so first, instead of actually having a high current, target current, high gate voltage to actually creating a conducting channel, this is actually gate will be actually a low voltage here, because now instead of having electrons, we're actually having positive charges actually flowing from source to drain, right? So we'll talk a little bit later, but PMOS is actually the opposite of NMOS. It is actually on when you apply a low voltage. That's actually when you have a conducting channel, and it's actually the voltage difference between source, and similarly, it's the voltage difference between source and the drain to actually create a channel. But PMOS is basically the opposite of NMOS here, right? So when we talk about behaviors, instead the voltage between drain to source, it actually source is a high potential terminals and drain is a low potential terminals. And similarly, source is a high potential terminals and the gate is low potential terminals here. So we'll talk a little bit more when we talk about PMOS and NMOS, but it is basically the flip version of NMOS. Okay, so we talk about, so far we have been mostly talking about planar transistor technologies, right? Everything is actually 2D. There's a source entering, there are channels conducted. When we actually like to more advanced technology, we talked earlier, right? So modern technology node is actually FinFET, right? And FinFET, the first FinFET patent was actually filed from Berkeley. So it's actually one of the most important patents actually in the semiconductor industry. So here, actually, when we talk about the channel length, right? So far, for most of the planar technology, a lot of techniques people are using is to actually shorten the channel length so that things can actually flow faster, right? To have actually more, and also denser. You can actually have more dense transistors being fabricated. But actually, when we get to the 3D technology, in particular, when we get to actually FinFET, it's getting very hard to do that because you can only shrink so small, right? When you actually get like very, very short channels, there are a lot of like non-ideal effects. It's very leaky. There are lots of behaviors related to short channel. What does the FinFET trying to do is that to try to still increase the contact area between gate and the, I guess, the body of the semiconductor, between gate and the belly of the semiconductor, but without actually changing or continuing shorten the length of the channel. What it does is that to have actually this kind of 3D structure, right? So you still have source and the drain here, but instead of just the bottom, it's like one-dimensional channels actually being formed. You can actually have this kind of a little bit awkward to draw, but it's like things are actually wrapped around the fin between source and drain. So there are like a lot more areas that are actually interacting between gate and drain. So there are like more conducting behaviors. The channels are better modulated between the different behaviors. So that's basically what FinFET trying to do, having this kind of interesting, I guess, weird things actually get started so that you have like better conducting areas there. And actually more advanced technology with this, what people call gate-all-around or GAA, is not only just the fins, it's actually trying to having even more contact area by having this kind of very weird, you can almost feel like breaks there, but then you can actually wrap around all the different dimensions. So there's like still, I guess, more channel areas being conducted, but not as significant but not actually keep shrinking the channel length. So that's like some of the more advanced fabrication folks are trying to do these days.
So they all around have less contact coating than
Because
it's less like source and drain touching.
but it's actually all the four edges are touch. You think about the bricks, it's like all the like surface area are actually touching there.
In these diagrams, the gray parts are going through the green parts.
Yeah, it's going through, everything going through there. So that's, it's an entire surface there,
Got it.
right? It's the entire surface here. It's the other way of viewing, if you look at the planar technology here, we have been actually looking at the cross section here. That's the dimension that we're looking at when we talk about planar technology. So now everything is actually contacted now through the entire green area.
So,
Yeah.
so for the is the gray part going through the
It's just underneath.
Yeah, it's going through
so at the top of the gray part touching. Exactly.
the bottom, yeah.
Okay.
So in planar, we're only getting at the channel from one side. In FinFET, we're getting at it from three sides. Get all around, you get it from all four sides.
And with multiple.
Okay, maybe there's like other stuff, but like if I have 4 different like gray parts, how do I make sure they're all like sensible like part of it? Is it just like connected on the ends, like drop connected to each other?
Yeah, those, I guess I don't know actually how the fabrication is done, but they are actually the same contacts actually being applied for. They're the same terminals aggregated together. It's pretty cool, I guess, how those like more advanced technology works there, Adam.
Is the gray bit made of dope silicon or polysilicon or what?
The gray part is actually the source and the drain.
Right, but like are they connected in the middle? Wouldn't they just always conduct that?
That's a good question, actually. So the gray part is a doped region. And okay, so there is, I think it's not drawing here, but there is still an oxide layer is actually, so you get the fin first, but you still need to do an oxide layer actually on top of the fin, and then you actually apply the poly.
Okay.
Yeah, so there,
It looks like you should be able to draw a line from where it says source to where it says drain, going only through the gray doped stuff, and then that should always conduct, right? Because it's doped.
you have the source and the drain here. But before before you actually reach the gate, there's still let's say the oxide layer here.
Yes,
So-
sorry, but between the source and the drain, ignoring the gate, it's
Okay.
just, it's a chunk of doped silicon. It should conduct, right? Even when
Oh, you're saying those two are, it's like always conducted in this case.
that's what I mean. Maybe I'm missing something in the paper.
Maybe like think of it as like there's a hole between the two sides, like gap. Like so it's just like a little bit inside the gray part.
So no, I think what you decided to top, there's another kind of building.
Okay, okay,
Sure, so if you remove the green part, it is a sense design, still like the MPS or kind
I
of.
see. I see. Okay.
Oh, interesting. Okay, so inside the gray part, there's still the body part there. Okay, oh, good to know. I see. Thank you. Interesting. So that's why it's very hard to fabricate. There are a lot of complexities to fabricate devices like this. Good discussion today. I also learned something today. Yes. Okay, I guess any other questions before we move on? Okay, I guess announcement, we're doing the last lab this week. We're going to wrap up the lab this week, and we're going to release the project next week. So we'll start project phase next week. So before that, we do have a buffer this week. We're not going to release new lab, so use that week to catch up. And we have midterm scheduled at this point in 3 weeks. towards the end of the October, and it will cover lectures up until next week. So cover basically all the combinational and the FSM, RISC-V, and some part of the CMOS discussion there. There's something there. Yes, we're aware of that. We're securing a room so that we're going to schedule for students who have a conflict with 189. We're going to schedule an alternate exam right before the regular exam. Yes, so stay tuned. Are there a lot of students have this conflict? What's that? It's good. Yes, we're trying to accommodate that. And how many students actually have this conflict? Oh, okay. So it will be right before the regular exam to guarantee, I guess, exam security. We'll probably have some hard constraints that you folks cannot leave until 5 or 10 minutes before the end of the exam. But we're scheduling an alternate exam. Yes. Okay, and right after the midterm, the Thursday of the midterm week, we'll have a guest lecture from Apple. And this has been a guest lecture we have been inviting for almost every year on FPGA emulation. It's pretty cool topic, and the speaker is also really good, and he's actually very familiar with, I guess, Berkeley students, in particular 151 students. So we are very excited to have him again, like Dr. Jay Moon, and he will be giving the guest lecture this week. I guess the lecture after midterm, so that everyone get a chance to relax there. Yes. Any other things you folks have in your mind? Questions, thoughts? Okay, great. So we talk about, I guess, the first part of the transistors, how we actually think about use transistor as a switch, and how we actually think about both NMOS and the PMOS. Next, we're going to talk about how we actually construct the PMOS and NMOS together as a CMOS gates. So when we think about like what we discussed earlier, right, we are really thinking about transistor as a switch, and then it's basically resistors. As like once it's on, it can be used as resistors. But when we actually think about switch, there are some actually like voltage behaviors that affect how good it is in conducting or transmitting different values. In particular, actually, when we think about in voltage, instead of just I guess a switch abstraction, let's see when we actually think about an NMOS device. So here's our NMOS device. Here's our gate. Voltage applied, we mentioned that when voltage applied, the switch is on and the current actually going through that, right? So here, if we actually have a NMOS device, when we have a VDD, the gate is on, the current is there, we can actually, the voltage is actually, we can actually discharge the capacitor here, and the node, the voltage here, basically the output voltage actually get to ground. This is 0, right? So this is a clean 0, perfectly actually discharged to the ground, and this is a behavior that we'd like to have, right? But what if actually instead of actually discharge the output node to 0, what if we actually want to use NMOS as a switch, but actually charging the output node to VDD? So in this case, again, we can actually have our NMOS device. We have VDD applied here, and we have our like NMOS applied, and the drain is actually connected to VDD here. Right here, all we discussed earlier, right? The gate is on when we actually have the gate voltage is high, and when we actually have a channel between drain and the source, and then we can start charging, right? Right, everything is so good so far. But the question is, when we actually do the charging, when we actually charge the output node to VDD, does it actually reach VDD? Can it actually reach the perfectly high voltage that we discussed before? No, because there is some internal resistance. Remember, we talked about the voltage difference, right, between the 3 terminals. We talk about actually when the gate is on, right, when the switch is on, we need to have the gate voltage, the voltage between gate and the source need to be greater than the threshold voltage, right? So that's a condition when we actually have a conducting channels. Remember, the gate voltage need to be actually higher and by the source voltage by the VTH, the threshold voltage, that's how we actually have the conducting channels. So now if the output node is connected to the source node here, right? So for NMOS, electrons is floating through from source to drain, but the current is actually flowing from drain to source. So here for the source node, to have actually a conducting channel, there is actually a voltage difference between the gate and the source. And now the gate is actually VDD, which basically means for the source node, the voltage is always, can only get to VDD minus VTH, right? So it cannot reach the perfect VDD because the voltage actually, the voltage difference between the gate and the source node, which is the threshold voltage that we discussed earlier between the source terminal and the gate terminal. Does it make sense? Right, so before, when the output node is actually, connected to the drain side, right? So for the first part, the output node is actually connected to the drain, so we can actually fully discharge to 0. But now when the output node is actually connected to the source, that's the threshold voltage difference we have. Is that going to do, yeah, that's a good question. Is that related to the saturation region or the others? We talk about 3 regions, right? Whether a gate is conducting or not, the flat region. Let me have my. So we talk about IV characteristics, right? Talk about this is the first region when the gate is not on, and this is the second region and the third region. So what is this actually related with? We're talking about the gate voltage. Gate to source voltage need to be greater than threshold voltage to even have a conducting channel there, right? And that is the first region we talk about, right? So here the behavior is actually related to the first region, and this first region is the gate to source voltage is less than the threshold voltage, then things are not conducting there, right? So here, this requirement is basically the source to gate voltage need to be greater than threshold voltage to have a conducting channel. So now if we are for NMOS, if our output is actually connected to the source node, it's actually not a perfect VDD. It's actually VDD minus by this like small threshold voltage that are controlling the channel here. Does that make sense? Okay, so that's actually when we think about, so it's really good at getting 0. This is good. But when we're actually getting 1, right, this is not a perfect 1. This is actually a non-ideal 1 for NMOS to be used as a conducting device. And similarly, we can actually see how PMOS behave here, right? So we mentioned that PMOS is basically the opposite of NMOS, right? So here, instead of having VDD to turn on the switch, we actually connected to ground to turn on the switch here, right? So here to turn on the switch, we discussed when we have a ground voltage, this is on, so it's always source to, and so here we are talking about hose here. So right, we have current now flowing from source to drain, and we are able to actually charge this to VDD, right? Because it's actually connected to the drain node, there's no threshold voltage requirement there. But when we actually apply this as a discharge, when we actually apply this as a discharge component, when we actually want to discharge the circuit, right? So when we actually apply a 0 here, things are actually discharging again. There is a source and gate voltage difference. It will not actually get to a perfect 0. It will actually discharge to a very small like threshold voltage here. So this will not get to a perfect 0 either. So it's actually, so when we actually charge it, you can actually fully charge to VDD, right? Because drain is actually connected to the output node. But again, when source is actually connected to output nodes for PMOS, we're actually discharging, and then we're actually cannot get to a perfect 0. There's always a small threshold voltage there. Am I getting you folks confused here? Questions? Thoughts? Yeah, what would you prefer, right? So here it get a good VDD, but it doesn't actually get to a bad. Yeah, what would you prefer when in reality when you actually use a PMOS and NMOS device? Where do you want to use those devices? There are non-ideal behaviors there.
Oh, you want the 0.
So you always want good ones, right? Right? So you want the device, when you want 0, you want to have a clear 0. When you want a 1, you want to have a clear 1, right? You don't want to have this kind of, oh, it's not 0, there's still a little bit of threshold voltage there. When you have 1, you want to have a perfect 1 so that you can actually propagate things through, right? So when you actually think that, so when we actually, that's why it's actually really good to use PMOS to transmitting ones, because you will actually get a perfectly charged 1 as drain node. Again, drain node is connected to the output node, and you also want to actually have NMOS to help you to actually get to a perfect 0, because again, you want the drain, basically you want the drain node to connect it to the output node so that actually the output node is not limited by the gate and the source voltage difference, the threshold voltage difference there. So in reality, when you actually want PMOS, you want it to use when you actually to connect to VDD so that you can connect to get good ones. And for NMOS, you want to actually, the source is connected to the ground, so you can actually fully discharge that. So that's, if you actually recall, we draw a lot of inverters before. What we always see is we have PMOS on the top, which can give us good ones when things are conducting, right? So we can have actually a good ones, and we always have NMOS at the bottom. So when things are actually conducting, we can fully discharge the charges and we can get a good zeros, right? So that's actually, we'll talk about more pull up and pull down network. So that's why things are called CMOS, because you want to actually have PMOS to give you on top as your pull up network. You can pull up to actually good ones, good high voltage, and you want to have the NMOS as your pull down network. So when you pull down, you can actually have a good zeros. So that's actually when we talk about complementary MOS transistor, it has both CMOS and PMOS, right? So PMOS is used as your pull-up network to actually get good ones, and NMOS is used as a pull-down network to get your good zeros, right? So here you will look at behaviors of our inverters, right? So when we actually have, let's say when we have 1 here as our, let's say when we have VDD here as our input, which transistor is on, PMOS or NMOS? NMOS, right? So it's high voltage, NMOS is on, PMOS is off, right? So NMOS is on, and that's how we actually, so the output is connected to ground. So that's how we get actually a 0. And this is a good 0 because it's actually connected to the drain node. And if the, let's say if my input is actually ground, or if my input is actually 0, and which transistor is on? PMOS is on, right? Because PMOS is on when the gate voltage is low. And we actually, so the output is connected to the VDD. So we get a 1 here. And PMOS is really good at transmitting 1, and NMOS is good at transmitting 0. So that's how we basically get values is inverted, right? From input to output. When you get a high voltage in the input, you get a low voltage. When you get a low voltage in the input, you actually get a high input, right? So that's basically when the input is high, you can basically think this is only your NMOS is connected. When the input is low, and only your PMOS is connected. That's how values are inverted, right? That's how we actually use both PMOS and NMOS to build inverters. Does it make sense? Okay, so this is actually how we construct CMOS circuit, having a both combination of PMOS and NMOS devices here, right? So now if we think about digital circuit, we start with our logic representations using Boolean expressions and the truth tables. When we actually build things in hardware, right? There are actually different ways. We talk about different transistor technologies. Even for the same transistor technology, there are different libraries associated with different library, right? So when you think about transistors, they're always like different metal layer stacks. Even for, let's say, 16 or 7, right? They're like for different library, different flavors of transistor. You can have a flavor that support more metal layers, have fewer metal layers. Those can have different implications on the density of the hardware you construct. We haven't talked too much. We talk about threshold voltage, right? But even for a particular design or particular node, you can actually have different threshold voltage associated with the transistors that also lead to actually different behaviors of your circuit. And finally, we haven't talked too much about the size of transistors, which actually have very big implications on both power and latency. We'll talk a little bit more next week and how we actually sizing the transistors and what's the timing implications of different transistor, different sizes. All of those are actually, again, even for a particular technology node, there are many different flavors of transistors, high density, low density, high metal stack, higher number of metal stack, smaller number of metal stack, different threshold voltage, different sizes. Those all contribute to different flavors, different component of your library, right? We talk about gate sizes, right? When you talk about inverter, some folks in the ASIC lab probably see like the transistors are different sizes, right? We'll talk a little bit more, but it's basically the different width. Like the channel length is like the gate length is always fixed, but when you can modulate is basically the width of the transistor. You can have like wider connections that has higher currents that can drive actually things faster and slower that also have different latency implications. So when we think about transistors, there are actually a lot of different flavors. We talk about something like very, very basic ones, but there are different ways. Think about different libraries, different components, and we'll talk a little bit more about the sizing implications when we get to the latency part. I guess we're halfway through the transistor. We already hinted a little bit on the pull up and pull down network. How about this? Well, let's do that next week when we actually review a little bit more, and we'll talk about the pull up and pull down network and how we construct more complex CMOS gate using both NMOS and PMOS. This is just a very quick overview of different components. I hope you folks get at least a high level idea of it, and we'll talk a little bit more about how we construct more complex gates and what are the latency implications next week. So good seeing everyone. Have a good weekend. I'll see you next week.